So, where are we at? I don't know how many of you have seen our previous webinar we had in November. We spoke about CVII and data, but basically we are moving forward in the industry. We're moving forward on working on solving some of the fundamental issues when it comes to standards around data and services. And I'm going to give you a short introduction to the CVII, and just as an introduction to the work that we are focusing on today about standardizing services. So first, a quick recap. The Common Vehicle Interface Initiative was started in order to talk about these fundamental issues about a common data model across the industry and eventually also a services model. Now, it is an initiative that moves from general trends and interests that we saw to an organized collaboration. And W3C and GENIVI started this this outreach to the rest of the industry. We did that driven by OEM supplier needs. We have had tier 1 suppliers working on specific projects aimed to manage the fact that there's too much unnecessary diversity across all of their customers, their OEM customers. And we've had a number of OEM roundtables where we speak with OEMs directly about their needs and their support for this idea. The key point is the fact that it's an outreach to other organizations in the industry. We want to deliver an industry common data model, a catalog of standard data definitions, and over time also follow up with a services model, which we will talk about today, and it's making progress very fast, as Magnus will give us all the information on this later today. And eventually, this can lead to also building a robust technology stack together, which is also a tremendous effort to do individually, and definitely worthwhile to solve the fundamental building blocks for data and services. So breaking that down a little bit graphically then, we speak about models. You may call them meta models, as the model that describes the model. It depends on your point of view, but it really boils down to how do we describe a set of data and a set of services. Once we have that agreed in the industry, we can work on standard catalogs. Standard catalogs means listing the specific data items or services that we expect all car brands to provide equally. And that means a standard API for all those functions where that is necessary or beneficial in the industry. Finally, the technology stack, as I mentioned, all of these possible types of software could be included in that. And that's something that is just fundamental, not really differentiating or shouldn't be differentiating between different parts of the industry. Instead, we can put our efforts on much more important parts. I'm not going to go through this picture completely, but the intention is really to show that there is the projects are ongoing. The initiative is about a year old now as under its current name. And a lot of these projects, some of them existed before and others are moving forward. So there is an organization that you can join depending on your specific interest. Let's talk briefly about the starting point for a joint data standard. So, as I said, today we'll focus on services, but we want to make sure you are aware of what comes before. The vehicle signal specification is a model and catalog based project. We say it's applicable everywhere, in quotes, because it is simple but extensible. So already today it focuses basically on the in-vehicle signaling, has a lot of the in-vehicle common information defined already, and It's been in development for several years. It's part of W3C automotive VISS specification, and we maintain the signal catalog in an open repository. There's then the VSS ontology. It derives from an extends VSS, and this, when you describe it with ontology methods, you can combine it with ontologies from other industries. There's a VSS layers concept that is about extending, being able to add extended metadata and deployment details. We may have time to get a little bit further into that later on. Finally, today's topic is about services, remote procedure calls, and full API descriptions. So that brings us from fragmentation to alignment. This is the key idea behind CVII. We're listing a number of organizations that you recognize here on the screen, and of course the list is not complete, but the key point here that I want to stress is that CVII is just not another project, but an initiative and outreach to the industry to really find alignment. And while we are proposing some starting points for the data model and services model, this is a very important part of the initiative itself, and that's why it's called an initiative. So finding the overlapping activities that we can talk about in search of this common goal, a consistent modeling standard. All right, so let's talk about services. Software complexity is SOA our savior. Here's a basic definition of SOA. A style of software design. Services are provided to other components through a communication protocol over a network. It seems almost incredibly simple, doesn't it? The definition. There's a part here also claiming that each discrete unit of functionality can be updated independently, and that's an interesting part to look into further. So in our opinion, SOA is required but not sufficient. So some of the reasons there's really not a single agreed upon way to describe service interfaces, first of all. We have some proposals, well, rather some options with Swagger and Open API and such things, but they are really focused a lot on the web-like RESTful interfaces. And what we are talking about is a more generic interface description language. Then SOA on its own, when people propose it, it seems to appear to a proliferation of interface definitions. It just promotes everyone to create lots of interface definitions, and then someone is left to integrate all of these. And integration work is not eliminated. So not only do we need a common model, we do need to complement this with a catalog of standard services so that that integration work can be done essentially once or to that effect. Just a little bit of an idea of what's software architecture for anyway. So I would propose that it's to manage the complexity inherent in the system. Now, when we do that, we talk a lot about how to build abstraction layers, how to ensure decoupling of subsystems. And why do we do that? I mean, think about it fundamentally. It is about facing technology diversity, and that's why you need the architecture to be there. If there was a truly homogeneous system, the architecture would almost fade away. And so when we talk about the architecture, it is to manage a complexity and a diversity of technology. And we talk about being prepared for change, which is also an effect of not being aligned on the fundamental technologies. And so that may make us feel better. What's an alternative? Maybe we don't focus on managing complexity, but trying to get rid of it. Now, if you think that sounds profound or just naive, it depends probably on your point of view. But I assure you, it's not naive from my perspective. I can see how so much effort is spent on unnecessary technology that isn't about the final function and isn't about true innovation either. And that's what we're talking about in CVII, to finally get rid of that in the in the automotive industry. So what can we do concretely? We use a single agreed upon way to describe interfaces and data. So what we call the models or meta models for data and services. So this is the how to describe all data and interfaces. Then we promote the development of standard catalogs for data and services. And that in turn will mean that basic commodity functionality truly becomes a commodity. It won't happen for everything, obviously, but movement in this direction is necessary. So to summarize, complex architectures exist primarily because of technology diversity and fragmentation in those details that we do not need to have fragmented in our industry. We should work towards facilitating development and reducing that complexity so that we can really get rid of the mess that we see out there in some cases. And that means we can put the effort on the real challenges, on the innovation, on the amazing challenges that the industry has for safety and cybersecurity and other issues that are so much more important. And it turns out also that once we agree on a way to describe data and services, only then can we develop a high quality technology stack together that does all of the heavy lifting of transferring data between systems, invoking services, and making sure everything connects together. And that's removing the duplication of this all too similar technology fragmentation that we see. So with that, I'll get off my soapbox and introduce Magnus to get into the really fun stuff and talk about what we can do specifically for services, models, and catalogs.
Thank you, Gunnar. Before I start, I want to build a little bit on what Gunnar said about complexity. We need to get rid of complexity, but we need to distinguish between being complicated and being complex. And I'm drawing this from a book called It's Not Complicated by Rick Nason, and he argues, and I agree with that a complicated system describes the components that are included in the system, 100 ECUs, and how they are arranged inside the vehicle itself. The complexity comes not from how many ECUs we have or what they do, but how they interact. And it's that interaction that today is handled mostly by CAN. I know we all try to get away from it, but we're still here. And which is extremely complex and error-prone and hard to maintain and interdependent and everything else. And that's what we need to break apart and start to separate the areas of concern into a service catalog with the underlying technology. So step off Gunnar's soapbox now and continue here on my end. So I'm going to go through the technical side of things a little bit, but I'm going to root it in the business side of things. And I need to find my clicker. Here it is. So we have a number of objectives for the vehicle service catalog. First of all is to specify a standard catalog of standardized services to drive the industry transformation to service-oriented architecture. We want to provide a higher starting point for all the industry actors, be it tier 1s, tier 2s, tier 3s, OEMs, outside people who want to get into automotive, fleet, commercial, etc. And we want to do that by defining a set of services that are non-differentiating, which means that they don't add, they're not a part of the secret sauce for a specific OEM. For Jaguar Land Rover, where I used to work, for that secret sauce, for example, would be the all-terrain drive system, the iDrive system, which never will be published. But on the other hand, the seats, HVAC, radio tuners, doors, ambient lighting, and things like that, they do add value, but they're not differentiating. Those are the standards that we need to standardize, or sorry, those are the services that we should standardize so that we all can work with a common perception of how do you actually do ambient lighting, how do you set specific colors, etc. We also want to specify on the W3C side a protocol for vehicle access from the outside. So how do you knock on the telematics unit and in a robust, safe, and secure way in order to access vehicle features inside that vehicle, and the other way around? How do you reach out from the vehicle to access cloud services for nav, AI, voice interpretation, etc.? So those are two standards. And the third standard is what this webinar, quite frankly, is about. It's about promoting industry adoption of standardized services and protocols and set up a neutral arena where we can collaborate on non-differentiating services so that we don't have to reinvent the wheel again and again and again when we send out our RFIs and RFQs. So I'm going to move on to that a little bit. So if we look at the drivers, I'm from the OEM side, so I'm all about the first one here. OEMs are now in a position when they're insourcing their stuff, their software development, and we're all doing it, to be able to own our own future, our own technical roadmap and our own software future, and we're kind of transitioning to a software first or software centric organization, and it's extremely painful all across the board that I've seen. If we can use standardized APIs, that's the first step for an OEM to be able to decouple enough from specific vendors. We'll still source the technology from the vendor, but we're going to integrate them ourselves into a functioning vehicle. The end goal here, at least this is my opinion only, is that an OEM should have enough ownership of its own system architecture and implementation so that it can replace major blocks of technology without external help. Do you want to replace the speech system? Please go ahead. Here's the API. Invite somebody else than your current vendor and challenge them with an SDK. Please show us something better. You have 3 months, and here's the vehicle, here's the SDK, here's everything you need. We also want to push for standard compliance, allowing us to do a side-by-side comparison with the tier ones, which obviously will change the relationship between the tier one and the OEM through contracts, through how sales are done, etc. But that's a key point as well, because today when bids come in, they are often very different based on different technologies. There's a lot of proprietary magic sauce. It's a sexy PowerPointer, but it's hard to do apples to apples. A standardized service catalog, especially if you go out in the RFI and say, please make sure that you're compliant to GENIVI W3C standard services, will make it much easier to compare those. I need to speed up a bit because I'm talking too much. And we can use open source standardized tools, etc., to create a higher starting point. So we don't, as I said earlier, reinvent the wheel, and we can focus the resources in the vehicle program on the important bits, which are the brand differentiating experiences, what makes us unique. For tier 1 and 2s, it's pretty simple. You don't have to customize your technology again and again and again, and then worse, maintain that technology and that specific customization for an OEM over the lifetime of a vehicle platform. You can now move closer to a product thinking where you take the 80% that's done and add the last 20% customization instead of the other way around, which I believe is the fact today. Less mitigates risk, mitigates time to market, mitigates cost. It's happy days all around. And again, you can compete on technology, not on non-scalable engineering effort. And for non-automotive drivers, this pretty much opens up for third parties and new services to access vehicles in a safe, robust, and secure way. So to try out new services, and you can approach the tier ones, you can approach the OEMs and say, hey, we have an awesome new way to remotely manage a vehicle, and we have a standard interface of doing it. So moving on. So why yet another standard? Well, automotive is a little bit specific, and I know all industries say that. The thing is that once a vehicle gets flashed, you now have 100, 150 ECUs, depending on which brand you are and how many ECUs you have, obviously. That is now a big embedded distributed system with no sysad being available to help. There's no IT support to call when your brake controller doesn't boot or your body controller doesn't unlock the vehicle anymore. It has to work. That kind of flashing and fixation of code, configuration data, and build data puts a couple of unique requirements on the IDL language, the interface definition language. So we need to make sure that we can handle that. But ahead of all, we also kind of not deploy this on a clean sheet. There's a ton of legacy things out there. So we need to be absolutely sure that we can handle and integrate with the existing protocols and languages that are running around out there, be it Franca, DDS, some IP, CanOpen, whatever, and not kind of force ourselves into an existing situation, because adoption will be zero. Nobody will pick it up because the barrier of entry is just too high. And as I mentioned, we have a very complicated and today complex system. We're trying to reduce complexity. And we need to be able to handle namespacing, IP address management, and other data that are frozen in place, build time, when all these ECUs are connected together in the vehicle itself. It has to be lightweight. Today, you need to be able to offer up a bit of value in about 5 to 10 minutes. People need to get it immediately on the documentation side, download it, open source, go, oh yeah, this is really cool, and be able to play with it without having to ask the manager. Almost all these technologies that I've seen deployed in vehicles lately come through a grassroots movement from the engineers themselves. It's almost never an order from high up going, you're all going to use this and this and this framework today. The innovation of how you deploy new technologies are almost all from a grassroots level when it comes to making life easier and making a more scalable and expandable system. And as Gunnar pointed out, we're not here to replace Frank IDL and, you know, the gRPC, flat buffers, whatever, all the million different things that are out there. We're here to integrate with them. We're here to be able to translate between them and offer a path to people who are already using it to be able to talk across these services. You're not bound to. Some usage examples, I will start to speed up here. And I will speed up a lot more on the actual technology. If you have questions about what I'm doing here, please ask them, and I'll be happy to go back and revisit here. So one example you have over here is that you have, I don't know if I can mark this, I won't even try it. You have this configuration service specification in the top left corner, and this is all about a configuration service. I want to store my favorite, I want to store my HVAC temperature that is in the vehicle when it turns on. I take the configuration service specification, I'll get to the format of that. I'll put it through the VSC Gen code generator, and it generates 3 files. Down to the bottom left, we have the configuration protocol library for Kotlin, and then we have the same for Python and the same for Rust. These 3 generate 3 different language bindings, and more importantly, 2 different protocols, which allows you to mix and match protocols and languages in a way that I haven't really seen so far, because usually when you use gRPC or something like that, you get a fixed protocol and you get a fixed number of languages. If your language is not supported or you have another protocol, for example dbus, you're out of luck. What we can do here is that you can add your own language support and your own protocol bindings fairly easily, and I'm going to show how that's done. At the end of the day, you will get all the code and protocols you need in order to write 3 fairly small apps. 1 remote configuration for your mobile phone left. In the middle, a user profile manager that sits in a central ECU somewhere. And then on the right, we have the IVI system where you actually do the settings side and everything else. So it's all described through single services, but we have multiple targets on language and on protocols. And in a similar way, we can run permutations on this. Here's an example where you bring your own device, BYD, and you have a small Kotlin app to do ambient lighting. Now we can have an external surface in the vehicle toward the local Wi-Fi, and now you can do a set value through gRPC, for example, and I want to set a specific color with the intensity 5. Single service, you decide the target language and obviously the target environment and also the protocol that you want to use. And the next one is we are, through W3C, we are primarily targeting external code, external communication between the vehicle and some kind of external entity, most likely the cloud. However, from a purely service point of view, it's the same thing. It's just a different level of real-time, robustness, security, etc., persistence, and all that. So you can have the same example and the same code and the same tooling, but just with a different backends. So now we need some speed here. We have 2 different ECUs. We have the central power ECU that cycles up the vehicle through power states, and you have the body controller. What you can do here is that now you start generating some IP methods instead with service IDs and method IDs and payloads. And then again, from the application you write, you now make local API calls on the power side, set power state 5, and you get a call on the right-hand side inside the power state manager of the door module that goes, oh, power state was just set to 5. Very nice. No protocol awareness, no network topology awareness, nothing like that. People can focus on what adds value, which are the applications, and do not have to worry about the hard to solve problem of service discovery, authentication, authorization, execution. That is code generated. And we do, to prove the point of being interoperable, you can translate from FrankIDL, for example, through the converter to vehicle specification and thereon move on. So if you're using Franka today and it is being used in industry, you don't need to throw that away and rewrite it. You can keep it forever, or you can choose to, over time, migrate to the vehicle service spec file, which I'm getting to soon. That's up to you. This could be, you could use everything that's generated as build artifacts and keep your Franka IDL specification as the single source of truth. That's what we want to achieve. And obviously you can go the other way around as well. So you want to be able to both import and export to different formats. FrankIDL is just an example here. This may just as well be in a gRPC IDL file if you want that. So if you start to look a little bit at the service file structure, it's nothing magic. It's not that we came up with the best idea in distributed computing and decided to make something out of it. We aim for simplicity, ease to understand, lower the barrier of entry. So with that in mind, you're looking at the structure. We have namespaces, which can be nested to arbitrary depth. We have a data type system that allows you to define structs, which can be nested, basic type def, just aliasing, and enumerators. And we have methods with in and out arguments, guaranteed delivery, and they don't have to return anything. They have one sender, one receiver. We have events which trigger action, so you get a callback when that happens. Pub sub, so one or more subscribers, one or more publishers as well. We are talking about properties right now. Again, this is under development, and we are in the middle of the engineering mudfest that's going on, and it's great time. I mean, it's really fun from an engineering point of view, and I invite you all to join us in our open meetings and kind of, well, join the wrestling. And it's giving good results, by the way. So this is what it looks like right now. We may hopefully, we are still discussing properties and how to kind of move to that as well. But this, we're starting to gel the overall structure of this, and we're quite happy with it. And then I'm going to go through this quickly. This is an example of the Python dbus code generation, where data types just gets generated as nested classes. So namespaces become just a class that hosts other classes. And then we have dbus becomes enumerators, et cetera, et cetera. So it's not specifically, again, it's no magic here. This is straightforward template-based code generation. I'll get to the templates in a second. We generate both the server-side code and the client-side code so that you pretty much get an API presented, depending on which side you are. You can make that call immediately. And as you can see, either you call your own implementation on the top for get config value, or you just call dbus to, if you're on the client side, to get that call over the wire. And I picked dbus in this case because it's well established, well documented, and people know how to use it. And finally, events. Pub sub, so we use the emit thing here, not guaranteed delivery, but that's actually totally up to the underlying protocol. So choose your underlying protocol wisely, that we provide the code to interface that protocol. Nested namespace, nothing specific here. What's important is that you can import files, and I'll get to that, into a specific namespace. So you build up a namespace tree, and you can now import, for example, global errors. You can import an interface file into that namespace, and it's local for that. But you can still refer to data types in other namespaces as well. Deployment file structure is a small thing with a huge impact. As I said earlier, we have many ECUs that get frozen and flashed at the production line, and we run diagnostics, and then off the vehicle goes. And often we do a software update at the port of entry before it goes off, or as a PDI, the pre-delivery inspection, but that's it. We need to be able to lock things down in this network during build time. So you can do it either during design time, then it gets built into API. We can do it to build time, which we're going to talk about here, or you can do it runtime, which are traditional configuration files. Runtime is not really an option for setting up a system because you got to be absolutely sure that every ECU boots comes up and works, or else, worst case scenario, you have a recall where people get towed back to the shop, and that gets quite expensive. So deployment file structure specifies deployment files are added build time to existing services, and it extends to services with information necessary to, for example, set up the IP addresses or do, in this case, the dbus interface, which we need it, but it shouldn't be in a configuration file, because if something changes that configuration file, we are toast in the vehicle. It's just not going to work anymore. So we have this intermediate one, and it comes from Franca IDL originally, and it's such a small piece, but it's pivotal in order to be able to scale and deploy a distributed embedded systems with hundreds of nodes, which is exactly what we're doing here. And imports, already mentioned it, you can, in global errors, specify a namespace, and you have a data type, which is incorrectly indented here, that has a result, and it can be OK, which is 0, and a bunch of other error codes. At the bottom half, you can now import global errors.yml and use it as a local argument or data type, or you can do your own type definitions and include it in a struct, etc. This allows you to do two things. First of all, global data, but also import the callback interface from a service. For example, a configuration value has been updated. The server may want to do a callback or send out an event to that fact, so people go, oh, somebody updated the HVAC temperature, I need to change that. That interface can now be imported, and it allows you to separate out services, both design time, but more importantly, build time in your CI/CD pipeline without having this massive file that defines everything. You can separate the files out into discrete services and have them reference each other as needed, but not more than that. I think I'm nearing the very end of this, and we're 32 minutes in. Template files. So we take the service definition file in YAML, and then we parse it, which is just a big Python object at the end of the day, and we feed that parse tree to a sheet up Python template library, which is off-the-shelf stuff. It's used for HTML. It works okay for this. Maybe better solutions out there. If you know one, please do tell me. And what we now can do is that we can start to generate, for example, the XML introspection file, which is needed by dbus, by just taking this file and feeding it to Shida, and all the non-bold text is text that is going in verbatim into the generated file, the XML file in this case. Everything that's highlighted is code that is replaced by, for example, the dbus interface, which you saw in the deployment file. This is actual code. You can use loops for command in interface get commands. So I want to iterate across all the commands that are given in the service specification file, and I want to emit a method with that name and the arguments, which is a separate loop, and then you're done. So this is a way to create a dbus introspection file. The Python dbus file is somewhat longer because it needs to generate all the Python classes that host this and some wrapper stuff and everything else. But at the end of the day, I think the Python code, and it works, is a couple of 100 lines long, 200 or 300 lines. So it's very easy to add your own support for your own language. I'm probably going to do C or C++ next, and also your own protocol that you want to do, either homebrewed if you want that, or just use vSOM IP, for example, or dbus, gRPC, whatever you have. That's the integration points to the protocols themselves. It happens in the template files. And we encourage people to publish the template files, but sometimes you want to keep that in-house because it's proprietary, you have your own protocols, etc. And that's fine too. You can mix the open and the proprietary services and template files. So what are the next steps? We've written some tooling to generate everything that you saw. All the code you saw here was picked up as artifacts from the tooling. The VSC to Gen exists. It's early. It's more of a discussion point and production code this time around. But we agreed on that we want to be able to try out different technologies before we commit, both in GENIVI and W3C. So that's why we wrote this. We're in the process of open sourcing that. There are some political/legal issues that we're working through. We're at the tail end of that. We hope to have it published within 2 weeks. I'm a bit optimistic, but still. And once that's out, then we can start experimenting for real with how do we going to integrate VSS signals, which is an open conversation. And instead of just talking about it, fun as that is, we can now check out the code, do a trial edition ourselves, point to it and say, how about this? Here, I did something over the weekend. Here we can import the VSS spec, and here's the code that it generates. And people can go, yes, or oh, no, or yeah, we'll try something else. We're going to write Frank IDL integration, which is not that hard because they're semantically almost equivalent. And we need, with Ted Guild and company, agree on what is the kind of official transport protocol that we want to use in order to transmit VSE. Again, we are completely protocol agnostic here, and there are so many good protocols out there, and we're not going to write a new one. I think we agreed on that. We just need to pick one. And we also internally, if we look away a little bit from W3C, need to look which protocols do we pick for in-vehicle communication between ECUs. And there are several there as well. And then obviously, we now need to create an initial set of services where we very much invite the rest of the industry and the community to come up. They don't need to be complete services, but just domains where they see a need for fleet management, for remote access in general, for new kinds of services that we want to move into mobility, etc. So that's where we are right now. I think this is very much the last slide.
It's really just an invitation to read the reference to material. There's a lot more there. I think you'll hopefully get some answers to your questions today, but you could really just scratch the surface today. And without reading them out to you, I just recommend you to go back to these slides and refer to the links we have when the webinar is over.